Okay, so we are in sections 5.3 and 5.4. So we're looking at torque, shear stress, angle of twist, power, and how all those are related. This is example 4. Okay, so we have a compound shaft driving several pulleys, segment 1 and 2. 1 and 2 of the compound shaft are hollow and aluminum with outside diameter and a thickness. Segment 3 and 4 are solid steel. The bearings allow the shaft to turn. Determine the maximum shear stress in the compound shaft. Determine the rotation of angle C with respect to A and E with respect to A. So we're going to find all those things and also draw all the diagrams that go with it. So we are going to go ahead and kind of divide our bar. So I can see that 4 is going to have its own torque. 3 and 2 are going to have the same torque, but probably won't have the same shear stress because they are different materials. They are, well, the stress has nothing with material. They are different diameters. One of them's hollow, one of them's not. So potentially, and then this has its own torque. So let's just kind of look over here and over here. So this is segment 1 and 2. It's hollow. It's got a shear modulus of 4,000 KSI. And it is, so if it's hollow, we're going to have pi over 2 C outer to the fourth minus C inner to the fourth. And if I look at my tube, okay, it looks something like this. Then an outside diameter of 3 inches. So I'm going to have a radius outer of 3 divided by 2, which is 1.5 inches. And a wall thickness. So this time I'm told that the wall thickness equals 0.125 inches. So I want to get that inner radius. It's going to be the outer radius minus the wall thickness. And that looks like 1.375 inches. So I now have my inner and outer radius. I have G, I have lengths. So if I need twist, I know that my length here is 72 inches, 36 inches, 54 inches, and 54 inches. On this side, we have a different material, and they are solid. So when we look at it, it has a 1.5 inch diameter. So I know that its radius is 0.75 inches, which is C. And it has that shear modulus of 12,000 KSI. And so now we've got kind of our material properties set up and our geometry set up. So now we have to find internal torque. So number 1, always, we start with equilibrium, which is statics, because we've got to find those internal forces. And just to recap, when we, have a beam system like we had in statics and we learned we could cut it, then as I'm coming from the left, I have internal normal, shear, bending moment, and what we ignore is that internal torque coming towards us. So the butt of my hand goes at the shaft, my thumb is following outwards, and I'm twisting towards me. So, if you wanted to, you could kind of say it's like a twist towards us. So because we're in pure, I think it said somewhere that's just, we're in torque, we're not looking at anything else, then all we're going to be finding is that internal torsion. So we are going to have to make some cuts. And I am going to take my Post-it note, because you all know how I love my Post-it notes. And I'm just going to start at the left. And here's my shaft. It makes a change there. So let's just cover it up. Let's draw a free body diagram. And when I draw a free body diagram, I have 95 pound-feet. That's not a great unit because we're in feet. Okay. Internal. Okay. Cover all that up. Internal. Right hand rule, the butt of my hand sitting right here. So I know that twisting towards me, torque ED, that's assumed positive, okay, for behavior. Now, when I go to sum my torques, I'm just going to use, because I just don't want to have to come towards me, that's positive direction. So I have a positive 95 pound-feet, okay, minus that internal torque equals 0. So we get that internal torque equals 95 pound-feet, and we're going to need to change that. So there are 12 inches per foot. And we'll get that value in just a minute. Okay, so I get a lot of questions. Well, if it's positive, then why are we calling it negative? Okay, it's just like internal beam shear. Positive beam shear coming from the left goes down. That is positive behavior. It causes clockwise rotation of our segment. When I sum forces for equilibrium, I usually call up positive because that just makes sense. And if I were summing forces, equilibrium-wise, it is negative. This does not represent the behavior. This is just representing the crazy rule I have for what I'm going to call a positive direction. Okay, so positive behavior, but it's negative in terms of equilibrium direction. Okay, again, positive behavior, negative in terms of what I'm going to call positive for equilibrium. And it makes sense that it's positive because if we're rotating there, we have to be coming back equal and opposite to keep us in equilibrium. So we're going to move our paper down, and we don't have a torque change, no torque change till here. So both segments 3 and 2 will have the same internal torque. So again, I'm going to draw my free body diagram. I have 95 pound-feet. I have 270 pound-feet, and I can visually see which way this needs to go. But again, I'm going to assume positive. And that's going to be, and I guess maybe I should make them so they look the same kind of direction. So coming back towards me is positive. That is going to be torque from D to B. So now let's sum our torques. I'm going to call that direction positive. So I have 95 minus 270 minus torque dB equals 0. So my internal torque dB equals negative, okay, negative 95, 270 minus negative 175 pound-feet. And remember, we're going to need to make that into pound inches because we are in KSI, and we'll actually need to make it in kips and inches. So let's just erase these for now. We'll take care of our units later. Just be cognizant we need to fix those. So there is that. There is that. Okay. And I knew it had to be negative. I knew it had to go backwards because I could look at this and be like 270 is huge, 95 and something else is going to have to balance it, equal and opposite. But just let the statics do the work for you. Now we're going to come across, and I can draw this whole thing now. So I have 95. I have 270. I have a huge number now going backwards, 825. I'm going to assume positive by right-hand rule coming towards me, positive towards me, and that's from B to A. And then when I sum my torques, so I have a 95 minus 270 plus 825 minus TBA equals 0. So TBA equals, I'm going to take that over, becomes positive, and I get 90, 270 minus 825 plus, and I get a value of 645 pound-feet. Okay, which makes sense. If I've got 825, basically 925 going back, this 270 and this are going to have to be coming back, and that's positive. And so how could I check that? Well, I could always come from the right. So let's cover up there and just check going backwards. So I have an applied 650 right here. Okay, wait a minute. Did I mess up a number? Because it should be 650. So I should have 95. Did I write a number down wrong? 95, 270, 825. I just can't do math. 95, enter. 270 minus 825 plus 650. I don't know where 645 came from. I don't know. Pound, feet, but this is why I check everything. Okay, so I have 650. Now coming from this direction, if I put the butt of my hand up to, like right here, and go back, then I can see that that is positive. And now if I sum my torques, and we're going to go that way, is positive equals 0, I have torque AB minus 650 equals 0. So torque AB equals 650 pound-feet. It's positive. They are the same. So if you're struggling with this, just work it forwards and backwards. You should get the same values. So now that I have my internal torques, then I can start then determining what is my internal stress. So A, shear stress. And shear stress comes from shear stress equals TC over J for maximum. So let's look at this first piece. So if I want the shear stress from E to D, it's going to be that torque of 95 pound-feet, okay? And then I've got 12 inches per foot. And I'm going to have pounds. I've got 1 kip is the same thing as 1,000 pounds. So I'm getting rid of pounds, I'm getting rid of feet, and I will have kip inches. And then C, okay, that was given as 0.75 inches divided by J, pi over 2, 0.75 to the fourth. And if I multiply all of this out, I get 1.72 KSI. So my shear stress from E to D is 1.72 KSI. Now I can do the same thing from D to C. And here my internal is negative 175 times 12 over 1,000 to get it into correct units. And when I'm looking at D to C, I'm still with this solid over here, so I have 0.75 inches divided by pi over 2, 0.75 to the fourth, and I get negative 3.17 KSI. So this is the shear stress from D to C. And it makes sense it's negative because we're keeping up with our positives and negatives. So then I'm going to do the shear stress from C to B. And we still have that same negative 175, okay? But this time we have 12 over 1,000 to convert it to kip inches, right? Kip inches. But this time we have a different geometry. So the maximum occurs on the outside edge, 1.5 inches, divided by pi over 2, and then I have 1.5. Why am I trying to divide that? Erase pi over 2. My outside radius is 1.5 to the fourth minus my inside, 1.375 to the fourth. And if I multiply this out correctly, I get negative 1.35 KSI. So that's my shear stress from C to B. Okay, now we can go our shear stress from B to A. And we go to our torque, which was down here 650. So I have 650 times 12 over 1,000 times 1.5, that's the outer radius, pi over 2, 1.5 to the fourth minus 1.375 to the fourth. Make sure I do my algebra right, keep my extra parentheses there, and I get that my shear stress from B to A is 5.01 KSI. Okay, so I now have my internal torques, I have my shear stress, and so now it's pretty easy peasy to go back and calculate my angle of twist. I'm just trying to find another piece of paper here. Okay, so let's just cover this up right here. So we still have our givens and we still have our torques, and let's do angle of twist. So B, angle of twist, TL over JG. So let's just start at A, and if we're coming from A, then we're going to be twisting from A. So this is going to be like our 0 degree, and then we're going to be twisting as we come away from A, because it says from A with respect to A. So let's look at our angle of twist from A to B. Okay, so our angle of twist from A to B equals TL over JG. So A to B, I have 650 pound-feet. So I need to get it into kip inches. Okay. And my length is 72 inches over J is pi over 2, 1.5 to the fourth minus 1.375 to the fourth. And then G was given as 4,000 KSI. And so when we get this multiplied out, I get a positive value, so positive torque, positive shear stress, positive twist of 0.060067. And remember, our units are in radians. Okay, so now I can go from B to C. So we're just going back from A, but let's go from B to C. My internal torque was negative 175, 12 over 1,000. Its length was 36 inches. And then we have pi over 2, 1.5 to the fourth minus 1.375 to the fourth. We are still looking at this G of 4,000. And I get negative 0.008086 radians because I have that negative. Okay. Now we're going to go from A to B, B to C, C to D. So C to D, I still have that same internal torque of negative 175. We're converting it to kip inches, and it has a length of 54 inches. And I like when it's solid because there's just less places for me to screw up. That radius we had up here, right up here, see, 0.75. So I have 0.75 inches to the fourth, and we were given that its shear modulus is 12,000 KSI. So see, I'm like kips, inches, everything's in correct units, and it is negative, so I expect a negative rotation, 0.019014 radians. And then we can go from D to E. My internal torque was 95. And then I have 12 over 1,000. Its length is, see that, 54 inches. Pi over 2.75 to the fourth, 12,000. This time we get a positive angle of twist because we had that positive torque. So I have 0.010322 radians. Okay, so if I want to go angle of twist from A, okay, so that's like B with respect to A, well, A with respect to B. Well, we're going backwards. So now I'm going to go C with respect to A. So as I'm coming down, I'm going to have this twist and this twist. So I have 0.060067 minus 0.008086 equals, and I get, it's a positive value because this is much bigger, 0.052 radians. And that's the angle of twist C with respect to A. And then if I want the whole length, it's going to be E with respect to A. I'm going to add all of these up. So I have positive 0.060067 minus 0.008086 minus 0.019014 plus 0.010322 all in radians. So the angle of twist is 0.0433 radians. So even with all those negative torques in there, we still end up with a positive twist. So we can actually draw all this out. If I have my shaft right here, and I have 95, I have 270 coming back at me, I have a material change, I have 825, and then I have at the end 650. Well, I can draw my lines down. Choink, choink. That's where my material changes. Choink, choink. And we can do our torque, we can do our shear stress, and we can do our angle of twist. So my torque diagram, I found my answers in pound feet, so I'm just going to put this in pound feet. And as I go across, I had 95. We'll do these in different colors just to make it easier to see. So I had 95, positive. And then I went down to negative 270. Okay, so that's negative. So we've got positive area, negative area, and then I was way back up here with 650, positive. Then we calculated our shear stress, and our shear stress is in units of, we found our units of KSI. And starting at the left, we had 1.72, positive still, so we have 1.72. Then we went down to negative 3.17. Then we were at negative 1.35. And then we went back up to our positive of 5.01, so way up here. So here's our shear stress distribution. And now we can actually go back and starting at A, okay, starting at A, so everything was with respect to A, so we're going to start here at A. Then I'm going to go, okay, I'm twisting this much from A to B. So we're going to come up here to 0.060067. So we have that angle of twist. Then we're going to subtract off 0.008 because we're twisting back the other way, which we already said was 0.052. And then we're going to twist even more negatively back towards this. So we're going to be going down. And when we subtract that out, we get 0.033. So it's still up in the positives. And then we add that value on, and we end up at 0.0433. So even though we have the negative stresses in here and the negative torques, it still ends up being a positive angle of twist in radians positive. And that's where the twisting would end up. So this is how you can go back, and I don't know why that is so blurry. We will try to unblurry that. You can go back and actually sketch this stuff out just like you could with normal, like your normal force and normal stress. And when we do a bending, we'll have shear moment diagrams. We can also have shear stress and normal stress from bending and show how the deformation occurs.